1 gigabyte RAM. For smartphones and personal computers, 1 gigabyte of RAM was considered a meaningful step forward. It allowed devices to run basic operating systems with simple applications like messaging, music playback, and very light web browsing. At the time, software was far less demanding, and optimization played a major role in performance. Early Android devices and lightweight desktop systems could function reasonably well within this limit. This amount of memory was best suited for very basic tasks, such as reading text messages, playing offline music, or running single lightweight apps one at a time. However, multitasking was extremely limited. Opening just a few applications could quickly consume all available memory, forcing the system to close background tasks. This often resulted in lag, slow app switching, and occasional crashes. It was not suitable for modern web browsing, social media apps, or anything involving large images, videos, or background syncing. Even opening a modern website could overwhelm the system. At its limit, the device would begin freezing, apps would fail to open, and the system could become almost unusable. 2 gigabytes RAM. 2 gigabytes of RAM became the minimum for basic usability. It allowed devices to handle slightly more complex tasks, including improved web browsing, basic apps, and simple multitasking. Compared to 1 gigabyte, it offered a noticeable improvement in responsiveness, especially for mobile devices. Users could switch between a few apps without immediate crashes. Best suited for light daily tasks, such as messaging, light browsing, watching standard definition videos, and using simple apps. However, as applications became more advanced, even 2 gigabytes began to struggle. Switching between apps often caused reloads, and background processes were frequently closed to free up memory. It is not suitable for heavy multitasking, modern gaming, video editing, or running multiple browser tabs. Even social media apps with heavy content can slow the system down. At its breaking point, apps may stop responding, the system may lag heavily, and tasks like loading websites or switching apps can become frustratingly slow. 4 gigabytes RAM. As technology evolved, 4 gigabytes of RAM became the standard for entry-level systems. It allowed for smoother multitasking and could handle everyday tasks such as web browsing, video streaming, and office work. Operating systems became more stable at this level, and users could run multiple applications simultaneously with reasonable performance. This amount of RAM is best suited for general use, including browsing with several tabs, watching high-definition videos, using Office software, and running basic applications. However, performance still has limits. Running too many browser tabs, heavier applications, or background processes can lead to noticeable slowdowns. It is not suitable for demanding tasks like advanced gaming, professional editing, large software development environments, or heavy multitasking. At its limit, the system begins to rely on slower storage memory, causing lag, delayed responses, and reduced performance. 8 gigabytes RAM. For many users, 8 gigabytes of RAM has long been the ideal balance between performance and cost. It allows modern operating systems to run smoothly while supporting multitasking across multiple applications. With 8 gigabytes, users can open many browser tabs, stream high-definition content, and run productivity software without major issues. It also supports light gaming and basic creative work, best suited for everyday users, including students, office workers, and casual gamers. It handles multitasking comfortably and provides a consistent experience. However, as workloads increase, its limits begin to show. Heavy applications, large files, or running multiple demanding programs at once can push it to its edge. It is not ideal for high-end gaming, large-scale video editing, 3D rendering, or running multiple virtual machines. At its limit, systems may slow down, background tasks may close, and performance can drop when handling intensive workloads. 16 gigabytes RAM. As computing demands increased, 16 gigabytes of RAM became the standard for performance-focused users. It enables seamless multitasking and supports demanding applications such as modern gaming, video editing, and software development. With this capacity, systems rarely need to rely on slower storage memory, resulting in faster performance and smoother workflows. This level is best suited for gamers, creators, and professionals who run multiple demanding applications at once. It handles large files, complex software, and multitasking with ease. However, Even 16 gigabytes has limits when dealing with extremely large datasets or high-end professional workloads. It is not ideal for advanced 3D rendering, large-scale simulations, or heavy enterprise-level computing. At its limit, performance may drop when handling extremely large projects or multiple high-demand tasks simultaneously. 32 gigabytes RAM. At 32 gigabytes, systems move into professional-grade performance. This level is commonly used in video editing, 3D rendering, and advanced software development. It allows multiple high-performance applications to run simultaneously without slowdown. Large files and complex workflows become significantly easier to manage. This amount of RAM is best suited for professionals, including video editors, developers, designers, and advanced gamers who stream or multitask heavily. It is more than enough for most consumer use, but still has limits in extreme scenarios. It is not necessary for casual users and may still fall short for extremely large-scale scientific computing or enterprise workloads. At its limit, very large datasets or ultra-high-resolution projects may still push the system towards slower memory usage. 32 gigabytes represents a strong shift into high-performance computing. 64 gigabytes RAM. With 64 gigabytes of RAM, systems enter high-end workstation territory. This level is designed for extremely demanding tasks such as 8K video editing, complex simulations, and large-scale data processing. It allows massive datasets to be stored directly in memory, significantly improving speed and efficiency. This level is best suited for engineers, researchers, animators, and professionals working with large, complex projects. It is not practical for general users and is unnecessary for everyday tasks or gaming alone. Even at this level, extremely large enterprise workloads or massive AI training tasks can still exceed capacity. At its limit, performance bottlenecks may appear only in highly specialized environments with extreme data requirements. 64 gigabytes is built for serious professional work where time and efficiency are critical. 128 gigabytes RAM. At 128 gigabytes, RAM reaches enterprise-level capability. This amount is used in advanced workstations and specialized industries such as artificial intelligence, machine learning, and big data analysis. It enables systems to process enormous workloads and perform complex computations in real time. Entire datasets and projects can be stored in memory for instant access. This level is best suited for high-performance computing, AI development, scientific research, and enterprise applications. It is far beyond what typical users need. Extremely large-scale cloud systems or advanced research workloads can exceed limits. At its edge, only the most data-intensive tasks, such as training massive AI models,